This video is about energy changes in simple harmonic motion. We discussed energy changes in simple harmonic motion qualitatively in subtopic 4.1. We verbally describe these changes, and now we will also learn how to use equations to find the energy in a system that oscillates with simple harmonic motion. Based on the law of energy conservation, during simple harmonic motion, the total energy of the system is constant. Energy varies between kinetic and potential energy. At the equilibrium position, velocity is at its maximum, which means that kinetic energy is at its maximum. At the maximum displacement positions, the object stops for a moment, so potential energy is at its maximum. Potential energy for a simple pendulum is gravitational, and for a mass spring system, it is elastic. If you would like to review these concepts, feel free to watch the last video in subtopic 4.1. Since both the pendulum and the mass spring system have kinetic energy, while potential energy is different in these two systems, we'll focus on kinetic energy when developing the energy equations. We learned in subtopic 2.3 that kinetic energy is equal to 1/2 mv squared. Here m is mass and v is velocity. In the second video of this subtopic, we learned that velocity in simple harmonic motion can be calculated by using this formula. Here omega is angular frequency, x0 is the maximum displacement, and x is displacement at a given point during the oscillations. Let's substitute the expression for the velocity into the kinetic energy equation. This gives us that Ek is equal to 1/2 times m times plus minus omega multiplied by the square root of x0 squared minus x squared, and this is to the power of 2. Since we are squaring, we can omit the plus minus sign, square omega, and cancel the square root sign. This results in the following equation. As the object is passing through the equilibrium position, all of its energy is in the form of kinetic energy, so we can say that here ET, total energy, is equal to EK, kinetic energy. Moreover, at the equilibrium position, x, the displacement, is equal to 0. Combining this with the formula that we just found, we get that at the equilibrium position, the total energy is equal to 1/2 times m times omega squared multiplied by x0 squared minus 0 squared. Since 0 squared is 0, for the total energy we get this formula. Since the total energy of the system is constant throughout the oscillations, this formula can be used to calculate the total energy at any point during the motion. To find the potential energy at any given point, we simply need to subtract the kinetic energy from the total energy at that point. For completeness, here are the variables that are present in these two formulae. This wraps up our discussion of energy changes in simple harmonic motion and completes the final video of subtopic 9.1. In subtopic 9.2, we'll learn about single-slit diffraction.